Right. So the worksheet on sound, yeah, it's not that long, so it's okay that we had like 10 minutes overtime. So you have their intensities and intensity levels, speed. So the first question is about watts per meter squared and decibels, converting that, and also speed of sound. And then the second question is about Doppler effect. So those are the two most important concepts from this lecture. So again, as usual, yeah, let's start 11:30. So you have 20 minutes to go over the worksheet, try out the problems, or at least read through the problems. And at 11:30, let's come back. Let's look at the solutions to the worksheet. Okay, right? Sounds good. Yeah, before I forget, I should hit the record button. Yeah, so the first question is quite interesting. The mosquito, if you Google it, this device does exist, and it is being used. So this mosquito device sends out a high pitched sound, 17.8 kilohertz. And as we've seen in the lecture, as we age, the upper limit to the pitch we can hear decreases. So the older people sort of cannot hear these 17.8 kilohertz or 20 kilohertz sound, and they're not bothered by the mosquito device. But the younger people, like teenagers and such, they can hear this pitch, and it's a very high pitch, annoying sound. So we're given the frequency 17.8 kilohertz, and the first question asks us to calculate the wavelength of that 17.8 kilohertz tone. The sound, of course, propagates through air, and so the speed of sound in air is given as 343 meters per second. Okay, so we're given frequency. Don't forget the prefix. Okay, the unit for frequency is just hertz. So if you see any prefix before hertz, then you have to consider that as well. And the prefix kilo means 10 to the 3 or 1,000. So you should have a frequency of 17.8 times 10 to the 3 hertz. Okay? And the speed is 343 meters per second. Right, so the wavelength is related to the speed and the frequency from this equation. Speed of a wave is equal to wavelength times the frequency. And you can apply this equation to any kind of wave, sound waves, light waves, longitudinal waves, transverse waves. Yeah, and so we want to solve for the wavelength. So we need to isolate wavelength. We can do that by dividing both sides by f, because f divided by f is equal to 1. And so we now have wavelength is equal to speed over the frequency. And we know the speed and the frequency. And therefore, we can find the wavelength, 0.0193 meters. Okay, so as long as your frequency is in hertz and your speed is in meters per second, then your wavelength will have a unit of meters. Okay. All right, so the second question, we're given the intensity level. So again, whenever you have that word level, that will be the decibels loudness. So intensity level is 85 decibels at a distance of 1 meter from 1 unit. We want to find now the intensity, just the intensity, which is watts per meter squared. So this question sort of like already gave the answer. It says show that the intensity of the sound at 1 meter is 3.2 times 10 to the minus 4 watts per meter squared. So we sort of need to convert 85 decibels, and the answer that you get should be 3.2 times 10 to the negative 4 watts per meter squared. Okay, we've seen the conversion equations. Yeah. 1 times 10 to the minus 12, going from decibels to watts per meter squared, you have this log of, no, it should be the base 10. Should be the base 10 because decibels is log. So 1 times 10 to the negative 12 times 10 of the decibels divided by 10. So this is the equation you need for converting watts per meter squared to decibels. Okay. So beta, that's the decibels that you want to convert. Divide that by 10. Okay. Right, and you sort of need your calculator here. It's hard to do this manually because 85 divided by 10 is sort of 8.5. No, you can actually do the subtraction as well because you do minus 12 plus 8.5. But then you have to multiply that. You should have for the intensity. Yeah, cool. All right, so that question is just converting decibels, converting 85 decibels to watts per meter squared. And you use the equation with the base 10 to do that. Okay, the next question asks us to calculate the intensity, right? So there's no level. So intensity, it's watts per meter squared. Calculate the intensity of sound 12 meters from the mosquito unit. Okay? And we assume that the mosquitoes acts as a point source. It just means that you have there a source of sound, and the sound travels as spheres are centered around that source. And we want to find the intensity. And we learned, we've seen in the lecture that the intensity is related to the power at the source divided by the surface area of a sphere. Okay. Right, so to find the intensity, we need the power. Okay. The power is not given in the question, and we need R. R is the distance from the source, and in this particular question, it says that the observer is 12 meters away from the source, which is the mosquito unit. Okay, so for us to find intensity, we need to find the power first. We learned in the lecture that the power at the source is the same, regardless of your distance from the source. So we can find the power from the previous question. Find power using information from the previous question. So from the previous question, the distance is 1 meter, right? 1 meter away from the unit, the intensity level is 85 decibels. We converted 85 decibels to be 3.2 times 10 to the minus 4 watts per meter squared. So at 1 meter distance, we know the intensity, and therefore we can solve for the power. So power is equal to intensity times 4 pi r squared. Intensity is 4.02 times 10 to the minus 3 is what we solved previously, 3.2, sorry, 3.2 times 10 to the, yeah, I don't know where for. Yeah, previously it's 3.2 times 10 to the minus 4, actually. Okay, what's going on with my, so my iPad froze, just a minute. Okay. Yeah, 3.2 times 10 to the minus 4, that's the intensity. Three. Okay, times 4 times pi times 1 squared. Okay, so we're using the information from the previous question to find the power. The intensity at 1 meter distance is 3.2 times 10 to the minus 4. So so power should be equal to 4.02 times 10 to the minus 3 watts. Right, this is the power at the source, and the power is the same regardless of whether you're 1 meter away or 12 meters away. So we can use that power to solve for the intensity 12 meters away. So that will be 4.02 times 10 to the minus 3 divided by 4 times pi times the distance is 12. Don't forget there's a square. Okay, that should give you an intensity of 2.2 times 10 to the negative 6 watts per meter squared. Right. Okay, what is the intensity level at a distance 12 meters from 4 mosquito units? Okay, so what we solved here in question III is the intensity of 1 unit at 12 meters away from from 1 unit. So this is intensity of 1 unit, 12 meters at a distance, 12 meters away from the unit. Right. In the next question, we want to find the intensity level, that means decibels, at a distance 12 meters from 4 mosquito units. Okay. Right. So we learned in the lecture that we can add intensities in watts per meter squared and not decibels. So for 4 mosquito units, we assume that they're emitting the same power. They're emitting at the same power. So 12 meters away, they'll have the same intensity. Okay, so that means the intensity at 12 meters due to 4 units will be 4 times the intensity of 1 unit, right? 2.2 times 10 to the negative 6. Right? Okay. So then the intensity for the 4 units will be 8.8 times 10 to the negative 6 watts per meter squared. Okay, for four units, 12 meters away from the source. So we're assuming that the 4 units are all bunched up together so that it's just 12 meters away from all of them. Once you know the intensity in watts per meter squared, then it's just converting watts per meter squared to decibels. Okay. So the decibels is beta, and that's the one with the log. Log of the intensity you want to convert divided by 1 times 10 to the negative 12. So beta in decibels is 10 times log divided by log of 8.8 times 10 to the negative 6 divided by 1 times 10 to the negative 12. Should give you 69 decibels. Okay. All right. So the next question is Doppler effect. Okay. You have there an ambulance. So you have, say, an ambulance that's emitting sound. It's traveling down the road, say at 60 kilometers per hour. It's emitting sound at a frequency of 1,200 hertz. And then you have a car that's traveling in opposite direction as the ambulance. Okay, and the car is moving at 50 kilometers per hour. The sound propagates in air, so that's the speed of 343 meters per second. And the question asks, what frequency will a passenger in the car hear as the car and the ambulance approach each other? Okay, right, so that's the scenario. Do you think the passenger will hear a sound, a frequency that's greater than 1,200 hertz or less than 1,200 hertz? Yes, good. Yeah, so they're moving towards each other, or at least the car is moving towards the source, or the source is moving. Yeah, the key word there is towards, right? Movement is towards. Yeah, so since movement is towards, the frequency will be higher because sort of the wave is compressed when you're moving towards. Okay. Yeah, it's good. Congratulations. Yeah, it does. It is reassuring if you're getting it. It's less stressful, isn't it? Okay, to solve the actual frequency, the first thing you need to do is to check your units. Notice how the speed of sound is in meters per second. The speed of the source, so the source of sound is the ambulance that's giving away the sound, and the observer is the car. Their speeds are in kilometers per hour. So you have to convert that, convert 60 kilometers per hour to meters per second. Okay. And also 50 kilometers per hour to meters per second. Okay, the shortcut, if you're converting kilometers per hour to meters per second, is just to dividing by 3.6. Okay. So 60 divided by 3.6. 60 divided by 3.6 and 50 divided by 3.6. A 60 divided by 3.6 will give you 16.67 meters per second, and 50 divided by 3.6 will give you 13.89 meters per second. Right. So once you've sorted the conversion and you know the frequency will increase because it's towards, then the new frequency will be the one with the plus on top. Our equation divided by V sound and the minus at the denominator. And don't forget to multiply that whole thing with the old frequency. All right. Okay, so the sound, it's the speed of sound in air, which is 343 meters per second. Speed of the observer is the car, because the problem says that the passenger in the car hears the sound from the ambulance. So the observer will have a speed of 3.89 meters per second divided by speed of sound 343 minus the source is the ambulance, because that's where the sound is coming from. That will be 16.67. Okay, and then the whole bracket is multiplied with the old frequency, which is 1,200 hertz. Okay, bracketing is important in your calculator as well. So if you don't get the answer is 13 hertz, 1,313 hertz. If you don't get this answer, then play around with the bracketing. You might want to put a bracket here when you enter that in your calculator and a bracket below. So double brackets, maybe bracket 343 plus 13.89. Okay, that's the adding, divided by bracket 343 minus 16.67. That's the bracket there, and then times 1,200. 3.6. Okay, well, where did I? Oh, why 3.6? Yeah, that's a good question. So why 3.6? It's because kilometers. Let me just use a different sheets of paper. Why 3.6 kilometers to meters? If you convert kilometers to meters, you multiply by 1,000. Okay, and when you convert hours to seconds, you multiply with 3,600. Okay, so if you're doing kilometers per hour to meters per second, you sort of times 1,000, but also divide by 3,600. Okay, and if you do the inverse, because here you're dividing, so that means if you flip this, 3,600 divided by 1,000 is 3.6. Okay. Yeah, and so that's where 3.6 came from, is 3,600 divided by 1,000, and you flip that, and that's why you divide by 3.6. Yeah, it's a shortcut, so you don't have to do the individual conversions of kilometers to meters and then hours to seconds. Yeah, cool. Good.